Hey everyone, welcome back to the channel. In today's video, we'll dive into a key concept in Python that's really useful for interviews and everyday coding iterators and generators. These two terms might sound similar, but they're quite different in how they handle data. We'll not only explain the difference, but also go through code examples to show you where each one shines. Let's get started. Part 1, Introduction to Generator and Iterator. Alright, let's start with generators. Generators are like a fancy version of iterators, but with a cool twist, they're way more memory efficient. Think of a generator like a water faucet. When you turn it on, you don't get all the water at once, right? You only get water as you need it, and it flows when you ask for it. That's how generators work. They give you values one at a time, but they don't store everything in memory like a list or an iterator might. Let's say you're working with a huge file or you need to generate an infinite sequence of numbers. Instead of loading everything into memory and slowing down your program, a generator will just give you what you need when you need it. You can even generate endless sequences like Fibonacci numbers. Isn't that cool? Now, let's talk about iterators. Have you ever used a playlist on shuffle mode? When you want to listen to one song at a time, and once a song is done, you move on to the next one until the playlist ends. That's pretty much how iterators work in Python. Iterators allow you to loop through a collection of data like a list of songs, but one element at a time. For example, you can take a list and convert it into an iterator using the iter function. Once you have the iterator, you can access each item one by one using next. It's like hitting next on your playlist to get the next song. But what happens when you run out of songs? Well, Python gives you a heads up by raising something called stop iteration, telling you that there are no more items left. It's like when your playlist finishes and the music stops. Let's see some basic example. In this example, we define a generator function called count underscore up underscore to max. A generator is special because it uses the yield keyword to return values one at a time, instead of using return which would exit the function entirely. In the generator function, we initialize a variable count to 1, and in a while loop we keep yielding values of count as long as it is less than or equal to the max value. Each time the generator yields a value, it pauses the execution and retains its state. So when we call it again, it resumes right from where it left off. Next, we create a generator object by calling the count underscore up underscore up score tree function and assigning it to the variable counter. This generator object doesn't compute all values at once, it computes them on demand when we call next. When we call next counter the first time, the generator yields the value 1 and pauses. The second time we call next counter, the function resumes from where it paused and yields the value 2, and similarly for the value 3. After the generator has yielded all the values 1, 2 and 3 in this case, it raises a stop iteration exception indicating that there are no more values to yield. This is Python's way of signaling that the generator has been exhausted. In next example, we start by creating a list called numbers with the values 1, 2, 3, 4. A list is an iterable in Python, meaning it's a collection of items that can be looped over. However, to access the items one by one using Python's iterator protocol, we need to convert this list into an iterator using the iter function. Once we convert the list into an iterator using numbers underscore iterator iter numbers, this new numbers underscore iterator object allows us to access the elements one by one using the next function. Each time next numbers underscore iterator is called, it returns the next item from the list. For example, when we call next numbers underscore iterator the first time, it retrieves the first item from the list, which is 1. On the second call, it returns the second item, 2, and so on. This continues until all the elements have been retrieved. When we call next after the last element, in this case after 4, Python raises a stop iteration exception, indicating that there are no more items left in the iterator. This process is efficient when you want to handle items one at a time rather than loading the entire collection into memory all at once. However, iterators can only be traversed once, and when they are exhausted after stop iteration, they cannot be reused unless you create a new iterator or from the original iterable. Part 2, Simple differences. Alright, now let's break down the simple differences between generators and iterators in Python. To make things really clear, we're going to walk through these differences step by step, comparing them side by side in a table format. This is great if you want to quickly grasp the key contrast between the two. We will cover aspects like how they are defined, their syntax, how they handle memory, and more. Let's get started. Definition: a generator is a special type of function in Python that produces an iterable sequence of items, yielding them one at a time using the yield keyword. This means a generator doesn't return all its values at once, but instead returns one value at a time as you request them. In contrast, an iterator is an object that implements two special methods underscore underscore iter and underscore underscore next. These methods allow the object to be traversed one item at a time in a sequence. Both generators and iterators produce items sequentially, but the implementation is what sets them apart. Syntax: when you want to create a generator, you use a function with the yield keyword. Every time you call the generator, it pauses at yield, gives you one value, and then resumes when you ask for the next value. You can also create generators using generator expressions, which are similar to list comprehensions but more memory efficient. On the other hand, iterators are created by using the iter function on an iterable like a list, tuple, or string. Alternatively, you can manually implement iterators by defining both underscore underscore iter and underscore underscore next methods in a class. Memory usage: one of the biggest advantages of generators is that they are more memory efficient. Since generators only yield values one by one when requested, they don't load the entire sequence into memory at once. This makes them ideal for working with large datasets. Iterators, on the other hand, can consume more memory, especially if they're created from an iterable like a list that holds all elements in memory at once. This difference is crucial when you're dealing with large amounts of data or streaming data. State: with generators, the state is handled automatically. When a generator yields a value and pauses, it remembers where it left off and resumes from the same point when you request the next value. This means you don't have to worry about manually keeping track of the state. In contrast, iterators don't have built-in state management. You may need to manually manage the state when implementing custom iterators or handling more complex iteration scenarios. Lazy evaluation: both generators and iterators in Python support lazy evaluation, meaning they only produce values when you request them. This is useful because it saves memory and allows you to process potentially infinite sequences without overwhelming your system's resources. For example, a generator or iterator will only retrieve the next value when next is called, rather than calculating all values upfront. Use case generators are typically used in situations where you need to process large datasets or handle data that's generated on the fly, such as reading large files or producing infinite sequences. Since they don't store all their values in memory, they are efficient for scenarios that demand on-the-go data generation. Iterators, on the other hand, are more suitable when you already have a collection of data like a list or string and need to iterate through the available items. Iterators are great for when the entire dataset is already in memory and just needs to be traversed one step at a time. Part 3: hands-on examples for simple differences. In this example, we've defined a generator function called square underscore gen limit that yields the squares of numbers starting from 1 up to a given limit. The function uses the yield keyword to return the square of the current number num and then increments num by 1. This process continues in a while loop until the num exceeds the limit provided. After defining the generator function, we create a generator object called gen by calling square underscore gen3. This will yield the squares of numbers from 1 to 3. When we call next gen, the generator produces the square of 1, which is 1, and pauses. The next call to next produces 4 the square of 2, and the following call produces 9 the square of 3. Once the generator has yielded all the values, it becomes exhausted. If we try to call next gen again after our values are yielded, the generator raises a stop iteration exception, signaling that there are no more items left to yield. This exception is caught in the try except block, and we print a message indicating that the generator is finished. In next example, we are working with a string, which is an iterable in Python. The string ABC contains individual characters that can be accessed one at a time. However, to access them using Python's iterator protocol, we first need to convert this string into an iterator. We do this by using the iter function, which creates an iterator object called text underscore iterator. Once the string is converted into an iterator, we can use the next function to retrieve each character one by one. The first call to next text underscore iterator gives us the first character A, the second call returns B, and the third call gives us the final character C. After retrieving all the characters, the iterator is exhausted. If we call next again, Python raises a stop iteration exception, indicating that there are no more elements to iterate over. To handle this, we use a try except block that catches the stop iteration exception and prints a message letting us know that the iterator has no more elements. Part 4: Advanced and Complex Differences. Now that we've covered the basics, it's time to dive into the advanced and complex differences between generators and iterators. In this section, we'll explore the deeper nuances of how they work, such as their implementation, state management, performance, and more. We've laid these out in a table format to make it easier to compare them side by side. These concepts are essential to understand, especially when working with larger datasets or custom iteration patterns. Let's walk through each of these differences step by step to get a better grasp of how these two concepts operate in real world scenarios. Implementation. Generators are implemented using the yield keyword inside a function. This allows them to produce values one at a time and pause their execution after each yield. The generator resumes from where it left off when the underscore underscore next method is called again. This makes generators highly efficient for producing data on demand. In contrast, iterators are objects that implement both underscore underscore iter and underscore underscore next methods. These methods allow the object to be iterated over, but the iterator must handle state and progression through the sequence explicitly. Return type: when you define a generator function and call it, you get back a generator object, which is both iterable and an iterator. You can loop over this object using a for loop or call next to retrieve values one at a time. For iterators, they can be created from any iterable object like lists, tuples, or strings by using the iter method, or you can create them manually by defining the required methods in a class. Once created, an iterator will return one element at a time as you call next. Syntax: the syntax for generators is concise. You simply define a function with one or more yield statements, which pauses the function's execution and retains its state until it's resumed. This allows the generator to produce values on the fly. On the other hand, iterators usually require more boilerplate code because they need to explicitly implement both underscore underscore iter underscore underscore x methods. Alternatively, you can use the iter function on an iterable to convert it into an iterator. Lazy evaluation: both generators and iterators use lazy evaluation, meaning that values are produced only when requested. However, generators excel here because they don't store all the elements in memory, which is especially useful for working with large datasets. Each value is yielded one at a time. In contrast, iterators might hold all the elements in memory depending on what iterable they are created from, e.g., a list, which can increase memory usage. State management: generators handle state management automatically. When the generator yields a value and pauses, it remembers its position and resumes from there when underscore underscore next is called again. You don't need to manage any internal state manually. However, in the case of iterators, you might need to handle state management yourself or track where you are in the iteration. Additionally, you must manage when to raise the stop iteration exception when the iteration is complete. Reusability: generators are not reusable. Once they are exhausted, meaning they have yielded all their values, they cannot be iterated over again unless the generator is recreated. For example, once you've gone through all the elements of a generator, it's done. On the other hand, iterators can be reusable depending on the iterable. For instance, if you create an iterator from a list, you can call iter on the list again to get a fresh iterator and go through the elements one more time. Performance: generators are more efficient for generating large sequences of data on the fly, such as when you're reading lines from a large file or generating values dynamically. They save memory by only producing one value at a time, making them faster for certain use cases. Iterators, depending on the size of the iterable, can vary in performance. If the iterable is large and all the data is loaded into memory, iterators may consume more memory upfront compared to generators. Error handling: both generators and iterators raise the stop iteration exception when they've exhausted all their elements. However, with generators, this process is automatic once there are no more values to yield. Python automatically raises stop iteration. With iterators, if you're creating a custom iterating, so we click underscore underscore next, You need to manually raise the stop iteration exception to indicate the end of the iteration. Generator expressions with list comprehension. Generator expressions are a way to quickly create generators. They look very similar to list comprehensions. But the key difference is that generator expressions are more memory efficient because they don't store all values at once. They yield values one at a time. List comprehensions, on the other hand, create the entire list in memory, which can be costly if the list is large. Iterators are often created from existing iterables like lists, and since lists hold all their elements in memory, they consume more memory than generator expressions. Part 5, hands-on examples of complex differences. Alright, now that we've gone through the advanced and complex differences between generators and iterators, it's time to get hands-on with some examples. In this section, we'll demonstrate how these concepts work in real code so you can see the differences in action. We'll explore the implementation, memory usage, state management, and performance step by step. These hands-on examples will help solidify your understanding of the theory and show how to apply these concepts in practical situations. Let's dive in. Memory usage example. Alright, so in this example, we're creating a generator that produces a large sequence of numbers from 0 up to 999,990 day. But instead of creating a list that holds all these numbers in memory, we're using a generator to handle it more efficiently. Check this out, the function large underscore sequence is using the yield keyword, which means that it's only going to produce one number at a time when you ask for it. It's not going to generate all 1 million numbers at once, which would take up a lot of memory. Now, here's the cool part. We're using sys.getSize of gen to check how much memory the generator is using. And guess what? It's super memory efficient. The generator itself takes up very little space because it's not holding all the numbers in memory. It's just ready to generate the next number when we ask for it. If we were to store all these numbers in a list instead, it would take up a ton of memory. But with the generator, we get the numbers as we need them one by one without the heavy memory cost. Let's look into the iterator example. We're creating a large list with 1 million numbers from 0 to 999,900. Now lists in Python are iterables, meaning they hold all the values at once in memory. So when we use this list comprehension to build the large underscore list, it's literally storing all of these numbers in memory at the same time. After creating the list, we use this dot get size of large underscore list to check how much memory this list is taking up. And as you'd expect, it's going to show a pretty high memory usage because the list is holding all 1 million numbers in memory at once. The key takeaway here is that while lists are useful, they can become a problem when you're working with really large datasets. Since everything is stored in memory, it can slow down your program or even cause memory issues if the data is too big. That's why in cases like this, using something like a generator is often more efficient. State management example. So in this example, we've got a generator function called counter underscore gen. What it does is pretty simple. It starts with a count of 0, and every time we call next, it yields the current count and then increases it by 1. This continues until the count reaches 5. The cool part here is that the generator is automatically managing its state. Every time it yields a value, it remembers exactly where it left off. So when we call nextGen, it gives us the first value 0 and then pauses. The next time we call next, it resumes from where it paused. So it gives us 1, then 2, and so on. Unlike a regular function which would just return a value and exit, our generator hangs around, keeps track of where it is, and continues from there whenever you ask for the next value. It's like a bookmark in a book. You don't have to start reading from the beginning each time the generator picks up right where it left off. In the next state management example, we've defined a custom iterator class called counter iterator. It's designed to behave a bit like the generator we just talked about, but here we need to manage the state manually. When we create an instance of counter iterator, the underscore underscore init method sets the count to 0. The underscore underscore iter method simply returns the object itself, allowing it to be used as an iterator. The real magic happens in the underscore underscore next method. Every time we call next, it checks if count is less than 5. If it is, it returns the current count and increments the value by 1. If the count reaches 5, it raises a stop iteration exception, signaling that the iteration is over. Here's the difference. Unlike generators where the state like the current count is managed automatically. With an iterator like this, we have to manually manage the state. We handle the current value of count ourselves, and we have to decide when to stop by raising the stop iteration exception. So when we call next my underscore iter, it gives us 0 and then 1 and so on, but we're responsible for keeping track of what's next. Lazy evaluation example. Alright, so in this example, we've got a generator function called infinite underscore numbers. It's designed to generate numbers indefinitely, starting from 0 and going up forever. What's interesting here is that the generator will never need to actually stop, because there's no condition to break the loop. It will just keep generating the next number every time you ask for it. Now, this is where lazy evaluation comes in. The generator doesn't create all the numbers upfront. Instead, it yields each number only when you call next. So when we call next gen the first time, it gives us 0 and pauses. Then when we call it again, it gives us 1, and it will keep going like this, generating numbers one at a time. The great thing about this is that the generator doesn't take up a lot of memory, even though it's technically infinite. It's producing numbers lazily, meaning it only gives you what you need when you need it without storing all those numbers in memory. This is super useful when you're working with potentially infinite data, or when you don't know how many values you need in advance. In the next example of lazy evaluation, we're working with a list iterator, which is different from the lazy evaluation we saw with the generator. We have a simple list, my underscore list 1, list 2, 3, and we convert this list into an iterator using the iter function, creating my underscore iter. When we call next my underscore iter, it retrieves the first element from the list 1 and then the second element 2 when we call it again. The difference here is that, unlike a generator, this list iterator isn't lazy. All the elements of the list are stored in memory at once, and the iterator just goes through them one by one. So while an iterator allows you to access elements one at a time, the entire list still takes up memory from the start, because all its elements are already loaded. This contrasts with the generator example, where values are generated only when needed, which makes generators more memory efficient, especially with large datasets. Usability example. In this example, we are using a generator called gen, which yields values when we loop over it. We exhaust the generator by iterating through it with a for loop, which prints 0, 1, and 2, or whatever values the generator produces. Now, here's the key point about generators: once they're exhausted, they can't be reused. After we've gone through all the values in the generator is done. If we try to call next on the generator again, it raises a stop iteration exception, which is Python's way of saying, hey, there's nothing left to give. So in this example, after the loop finishes, the generator has already given us all its values. When we try to next gen again, we catch the stop iteration exception and print a message letting us know that the generator is exhausted and cannot be reused. If you wanted to go through the values again, you'd have to create a new generator. In the next example of usability, we're working with a list and an iterator. We first convert the list my underscore list 1, 2, 3 into an iterator using the iter function. Then we exhaust the iterator by looping through it with a for loop, which prints all the values 1, 2, and 3. The difference between iterators and generators is that iterators can be reused. Once we exhaust the iterator, we can reset it by calling iter on the list again. This creates a fresh iterator. In this case, after we've looped through all the values, we call iter my underscore list again to create a new iterator. And now we can call next to start from the beginning of the list again, retrieving 1. This is an important feature of iterator. It's unlike generators, which cannot be reused once exhausted. You can reuse an iterator as long as you call iter again on the original iterable, in this case, the list. Error handling example. In this example, we're working with a generator called general. Generators produce values one at a time, and we can consume them using next. But unlike a list where you know how many items there are, a generator produces values dynamically, so we need to handle when it runs out of items. We are using a while true loop to keep calling next gen to consume the generator. It will keep yielding values until it's exhausted. But once the generator has no more values to give, it raises a stop iteration exception, which tells us that the generator is finished. In the code, we catch the stop iteration exception with a try except block, and when it's raised, we print a message saying generator finished. This way, we handle the fact that the generator is done producing values and avoid the program crashing. In the next example of error handling, we are working with an iterator created from a list 1, 2, 3 using the iter function. Once we have the iterator my underscore iter, we can use the next function to consume its elements one at a time. But just like with generators, once an iterator runs out of items, it raises a stop iteration exception. This tells us that the iterator has been fully consumed. To handle this, we wrap the next calls in a while true loop and a try except block. The loop keeps calling next my underscore iter to retrieve each value until the iterator is exhausted, at which point stop iteration is raised. We catch the exception and print a message saying iterator finished. This approach ensures that the program doesn't crash when the iterator is done, and we gracefully handle the end of the iteration. Generator expression Z's comprehension example. In this example, we are using a generator expression to generate numbers from 0 to 999,999. This is similar to a list comprehension, but with one major difference: instead of creating all the numbers upfront and storing them in memory, the generator expression produces each value on demand. This makes it much more memory efficient, especially for large sequences. Here we're using sys.getSys of gain underscore xp to check how much memory the generator expression takes. Since it doesn't hold all the values in memory at once, it has a very small memory footprint. The actual values are only generated when we ask for them, which means this approach can handle massive sequences without consuming a lot of memory. If we were using a list comprehension, all the numbers would be stored in memory, which could become quite expensive in terms of memory usage. But with the generator expression, we only use memory for the generator itself, not for the entire dataset. In the example of list comprehension, we're using a list comprehension to create a list of numbers from 0 to 999,999. Unlike a generator expression which produces values one at a time, a list comprehension generates all the values upfront and stores them in memory. This means that while it's easy to access the entire list of values right away, it also takes up a lot of memory. By using size.getSizeOfList underscore conc, we're checking the memory footprint of this list. Since it's holding 1 million numbers, the memory usage is much higher compared to a generator expression. This can become problematic when working with large datasets because all the data is loaded into memory at once. While list comprehensions are fast and convenient, they come with a larger memory cost, especially for big datasets. This is where generators can be more useful. They only produce values when needed, helping to keep memory usage low. So to wrap up, we learned that iterators and generators are both ways to handle sequences of data in Python. But generators come with the added benefit of being more memory efficient and easier to write. They are a must-know for anyone dealing with large datasets or aiming to optimize performance per Python. I hope this video helped you understand the difference between iterators and generators. If you found this useful, make sure to hit that like button, subscribe to the channel for more Python tips, and drop a comment below if you have any questions or ideas for future videos. Thanks for watching.